2 quarks.
4 quarks.
4 quarks.
8 quarks.
8 quarks.
It would be
that would just
runaway.
keep going because it would
And the
continually
quarks would take over the universe.
That's it.
Ooh.
Damn.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck. Night, Chuck, baby.
Hey, what's happening?
When you got your little
I got my
tablet out.
My tablet.
That you know what that means?
Means it's cosmic query.
Cosmic queries.
That's
Brought
right.
to you by-
Inquiring minds want to know.
Indeed, cosmic queries. It's become one of our most popular formats.
Yep.
That's great.
I think people feel that they have a bit of control over the show.
Yeah. Is that why?
That's what
Is
it
that
is. Yeah.
Okay. Otherwise, we just run amok.
Right.
Okay. So we're here back in my office at the American Museum of Natural History, the Hayden Planetarium, where I serve as a director,
That's right.
right here in New York City.
Right.
All right.
And I serve in the cafeteria.
Stop. Want fries with that?
Yeah,
Okay.
exactly.
All right.
All right.
So just go right on in.
Okay, let's jump
do
into it. Let's
and it's
jump.
grab bag.
It is a grab bag,
Okay.
which we used to call galactic gumbo.
But why don't we call it that anymore?
I don't know what happened to galactic gumbo. People probably got tired of me going guarantee.
Isn't he dead?
I don't know. I'm not sure.
Paul Prudhomme, right?
I don't know if that's his. I don't know his name. All I know is
that's
he
his
used to
name.
be on PBS. He wore suspenders
And
and
he
be like,
weighed
no,
He weighed about 600 pounds.
Now, I got myself some crawdad here. No, this. We're going to add some drawn butter
Catch every eighth word.
Pigeon now, guarantee. He was like the James Brown of cooking shows. Hit over those cigarettes. That little bit just shoot the guy. Let them wheels him there. Get him with those guarantee.
If James Brown were Cajun,
James-
there's no
Cajun
understanding.
James.
There's no understanding.
He said you wouldn't understand a word he said. Yeah, but what I said, you. Yeah. Yeah, what do I get it? Yeah. Give me one of those, yo. A beep, 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 beep. Here it is. Mm-hmm. Here it is. You wouldn't know not one song. All right, here we go. Hello, Dr. Tyson, Lord Nice. This is Sarah coming from Austin, Texas. When we're talking about the age of the universe, 13.8 billion years, is the age of years in Earth years? Or is it the average time used? If it's Earth years, then wouldn't it be a different age of the universe depending on your location?
Yeah, it's Earth years.
It's Earth years.
That's not a unit of time we just all agree to.
Right.
And that exists as a unit of time right now, with or without the Earth.
Right.
We've defined it as a length of time measured by an atomic clock.
Right.
So if Earth got destroyed out of the solar system by some cosmic monster,
Ooh, that sounds like a good movie.
a day and an Earth would still be defined.
Okay.
Because we no longer rely on the rotation of
It's
the Earth.
not the rotation.
And the orbit of the Earth around
Right.
the sun
Right.
to reckon our accounting of seconds.
It's a standard unit of measurement.
Correct.
Okay.
So, yeah, it's just Earth years.
The same as inches and centimeters.
Yeah,
You know
you
what I
pick
mean?
a unit,
You
and
pick a
that's what it
unit,
is.
and that's what it is.
And
So-
you will get a bigger number in centimeters than you will in inches.
Right.
That doesn't mean the distance
But
is
the
farther.
distance is the same. You're just
Same.
measuring it in different terms. So it doesn't make a difference.
Correct, yeah. So nothing to lose sleep over that.
I like to use hands myself.
Oh, you
That's-
ride horses.
That's exactly. That's the distance that I use.
So you know how big a hand is?
No, I
4
don't.
inches.
That's a tiny little hand. who would measure hands like that?
No,
Like
4 inches. 4 inches. That's about. I think it's 4 inches.
that's like this much of my hand.
No, it's the width of your hand.
Oh, I didn't know
Jeez,
that.
gosh.
Now that I did not know.
You thought it was like a whole hand?
I thought it was a hand. You
No,
put a
whole-
hand and then a hand and a hand.
No, it's
Oh, it's like
sideways.
this.
Yeah,
sideways hands. Okay, well that makes a little.
yeah. I think it's around 4 inches.
4 inches. Okay.
okay.
There you go. That's how high you measure. The horses used to be measured from head to hoof. You know how many hands high they would
I'm
stand.
glad you didn't know that, because that would give me even more evidence that you did not grow up in the city.
I was born in the city.
Okay. More we learned about you. Well, when I was in prep school and I played polo, The stables had many horses. I said, who is my co-host
Who is
here?
this guy? All right. No,
My prep school chums were...
I did go to prep school, but that has nothing to do with my horse affiliation.
Your horse ignorance.
Yes.
Okay,
Right.
fine.
My horse ignorance comes from I used to attend riding camp when I was much younger.
Okay, all right.
So anyway, but it's been years since I've been on a horse, and the truth is, I think they're disgusting creatures at this point. But they are delicious.
Stop.
Please do not write. These are jokes.
Something interesting about a horse.
What's that?
Okay, so a human brain is about this big.
Okay.
You know how big a horse brain is?
No.
It's about the size of your fist.
Size of a fist. Yeah, because it's.
And they're a way bigger animal with a much smaller brain.
Yeah, well, I don't need them to solve calculus problems. My thing is like pull this plow. That's what I need you for. Okay.
And the horse is just fine with that.
That's it. All right.
What else you got?
This is Nobody. Hey, Nobody from nowhere, Vermont. Hello, Dr. Tyson, Lord Nice.
Wait. There's a character in West Side Story called Anybody. Anybody.
I did not know that.
Yes. It's a tomboy called Anybody.
Oh, really?
Yes. She wants to be with the gang. She
Oh,
got dirty face, short hair, wears pants, can fight, but they don't let
sounds rather sexy to me.
they didn't let her in because
Because she's a girl.
she's a girl.
Wow.
Yeah, back when things were quite binary.
I wonder, has gang protocol changed? Like if you're
You go to
if
the High
you're
Council.
like yes, I wonder if they're sitting around all the OGs and the young Gs and just like, have we advanced to the point where we can let girls in here and shoot them as well?
Do I? I'm just wondering if anybody's came from nowhere.
Oh, okay. So there you go. If anybody came from nowhere.
This person's from nowhere.
Nowhere.
Right?
He's from nowhere, Vermont.
Nowhere, Vermont. Okay.
No. So he says, hello, Dr. Tyson and Lord Nice. Is there any way for a non-physicist to correspond with a physicist about their papers without being a bother? Okay, I think this guy is angling to send you some discovery that he has, or he or she or
so
they
my
have
email
made.
is no longer public.
Of course.
It's no longer public.
No
It
longer.
was for a while.
For people like Nobody.
No.
Because of Nobody.
I don't want nobody
I
talking
don't want
to me.
nobody talking to me. Now, if you're somebody, we might be able to talk.
Had he been somebody.
Had he been somebody from somewhere, he would have got your email right here.
But now he's nobody from nowhere.
Nowhere, so you get nothing.
Sounds like an Abbott and Costello routine.
All right.
So almost every academic
Right.
on their university page has their email posted.
That's right.
Practically everyone. What you want to do if you want to correspond, if probably you have an idea, would you do some homework first?
Make sure.
Do some homework.
Right.
Don't go to them and say, I have an idea that Einstein is wrong and that all of you don't know what you're doing.
Right.
Listen to me.
Yes. And there are those out there.
Because you spent 2 hours watching a YouTube video.
Exactly.
And this person spent their life and career studying that one subject.
Exactly.
Okay?
Yes.
So just do a little homework.
Do a little homework. All right. And what you don't want to do more than anything
What?
is email Chuck Nice and say, Dr. Tyson is not answering my emails. That you do not want to do.
So that's how almost all of them, it's online. Almost all.
Right. Right.
Yeah.
Now,
Okay.
here's the thing. Correspond without being a bother.
Oh, without being bothered. Do your homework and
your
ask
homework.
an intelligent question.
Okay.
And don't tell them that you have a new secret to the universe and they have to listen to you. Otherwise, no, that is not humble. That is rather arrogant. That you, a non-professional, would know something more than the professional. So come to them a little more humbly. I have an idea.
Right.
It might be correct. I've thought about it in this way.
Right.
What do you think of it? And don't send them 20 pages. They won't have time for that. Okay?
Exactly.
And do your homework. Learn, buy some physics books.
Yes.
Learn
Right.
some physics.
Right. It's like going to a restaurant and just saying, oh, please, may I have a word with the chef? I'm sorry, but what exactly did you season this with? May I suggest in the future?
I know.
Perhaps some truffle butter would help, sir.
No, my favorite reply to that is, people say that you eat a great dish and they ask the person who cooked, what's the secret?
Right.
So you know what the answer is?
No.
The secret is 6 years of chef school.
There you go. That's a great answer too. 6 years of chef school.
You're thinking something tastes good because there's one secret
Right.
that they put in
Yes.
that you just learned that secret.
Right.
You could duplicate what they did.
Right.
Give them some credit
it's
for
a
expertise.
catalog of knowledge.
Give them some credit
Coupled
for
with
expertise.
skill.
Yes. Knowledge. Yes, you need the skill.
Skill. Right.
Yes.
All right. That's that's great.
Can you flip a fried egg with one hand while you're stirring something?
I can't even flip a fried egg, which is why I eat scrambled eggs.
It gets scrambled
en route. It gets scrambled en route to being flipped, and I'm like, well, we having scrambled eggs now. There you go. I'm not even joking. This is
all right. What else you got?
This is Mitchell Adkins, and Mitchell says, "Hello, doctor and Lord." Well, we're getting shorter and shorter, aren't we? This is Mitchell from Cincinnati, Ohio. I heard an old episode of yours where you talked about the spaghettification of particles at a black hole. You said that this continues all the way down until everything is ripped apart, which would make sense. However, quarks are held together with asymptotic freedom, meaning that the strong force holding them together increases the further you pull them apart. Would there theoretically be a point where the gravity ripping quarks apart would balance the strong force of asymptotic freedom and actually end up balancing and creating some kind of equilibrium?
Oh,
actually did a little homework
Oh.
to ask a question, knowing about the weak and the strong force and talking about the asymptotic freedom of quarks and particles. And
So let me tell you something about quarks.
This guy is good. Yeah.
You might not know.
Go ahead.
I'll tell you something about quarks. Okay. We've never seen an isolated quark.
Oh,
They come in pairs.
okay.
Pairs or more.
There you go.
Okay. So let's try to create an isolated quark.
Okay.
Quark. So you go down there and you get a quark pair and they're stuck together. You begin to pull them apart.
No! No! That's my brother! No!
You begin to pull.
No!
It's the soundtrack.
You're killing us!
So you pull it apart.
Okay.
And the force holding them together gets stronger the more you pull.
Yeah.
The greater is their distance, the stronger is the force. Wow. No, it's not that mysterious.
Right.
Name something every day for which that happens.
Magnets? No.
No, they get weaker.
In opposite.
They get weaker.
Something that you pull apart and it gets
stronger. Yes.
That happens every day.
You get it every day.
Every day as you pull it apart and it gets stronger.
Ding, 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 ding,
The absence from my children,
ding, ding, ding.
I'm going to go with yes.
No, a rubber band.
Oh.
You pull it harder, it's
and
a stronger
it creates
force.
more tension.
And the closer you're in, the less force there is.
Right.
And a spring.
Right.
Okay?
A spring. There you go.
Right. And mathematically, you can represent that with a very tidy formula. And the spring is what's called a spring constant. It tells you how tight it is.
Okay.
How much energy that takes. So we think of this as a spring. But here's the catch. As you pull them so much apart, at the moment it snaps,
right,
you have pumped so much energy into
pulling it apart,
that energy in that instant becomes two more quarks, and now you have two pairs of two quarks.
Yo.
It's diabolical.
That is crazy.
It's diabolical.
That is crazy.
It's diabolical.
So the energy that you
because it takes energy
separating the quark
equals MC squared.
Right.
Right at the moment, there's enough energy for each one
to create another quark.
It snaps.
And now once again, you got two.
You got two quarks.
You got hydra quark. Nice.
You got two quarks on each one.
Right.
Right. So quarks are diabolical in this way.
That's
okay. So he knows that as you're falling down, the tidal force is going to stretch you.
Right.
That's giving energy to the quark.
Right.
So he's wondering if there's some balance point down in there.
But now, here's the thing, though. As the quark gets pulled apart, okay, what happens is there is a point of breaking. So wouldn't you just start making infinite quarks?
It kind of seems that way.
Because
Chuck.
That's really, forget the equilibrium. We're not looking at equilibrium. We're talking about the creation of the quark. So what you would have is two quarks. Four quarks. Eight quarks.
And that would just
keep going because it would continually.
And quarks would take over the universe.
That's it.
Ooh.
Damn. It's your world. I'm just a quark living in it.
So, what we do know is there is no known force that can resist the gravitational collapse to a singularity.
Right. At some point, the immovable force whatever it's called. You know what I'm saying. What is it?
Movable object,
The movable
irresistible
object,
force.
It meets the irresistible
Yeah.
force.
So I don't have a good answer.
Wow.
It seems to me you would have a quark runaway.
Right. That's really...
I got to talk to some people about this.
That's just freaky.
I got to talk to some people about this.
Freaky, man.
I don't have a good answer for you.
Yeah.
Chuck just said the quarks will take over the universe, and I don't have a good rebuttal for that.
Yeah, that's so cool, though. I mean,
Yeah.
what a great thing to think about. All right, here we go.
Yeah.
This is Bobdan. Bobdan or Bobdan, okay?
Did he have
Bobdan all together.
Bobdan.
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 Okay, there you go.
It's not Bob Dan, unless the parents were lazy because they they want to name him after Grandpa and Dad.
Even though Bobdan is a great name when you're mad. Bobdan! Bobdan! How many times have I told you?
Bob, damn it! Come on over here. Okay. Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't
All right.
happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up.
A black hole is matter, energy, and radiation, all compressed down to a point of singularity where space and time cease to exist. On this flip side, a Big Bang is also a point of singularity that explodes matter, energy, and radiation out into a new space-time universe. So, why are the origins of Big Bangs and universes still a mystery? It seems logical that the Big Bang births a new universe. Space-times are simply black holes of other universes and space-times. Mystery solved, right?
Yes.
There you go.
Okay, next question.
There we go. Bob Dan.
So back on my shelf, I got a book by Stephen Hawking. Is the large-scale structure of space-time.
Okay.
It's got some title like that.
All right.
And in it, it describes the physics and the mathematics inside the black hole.
Okay.
And as you go through, it basically opens up an entire space-time. So inside a black hole is effectively a whole other universe, which leads us to wonder whether our universe is just inside somebody
else's black hole.
Somebody else's black hole, correct.
Look at that.
And we have a horizon that you can't get out of.
Right.
And there's stuff beyond it, but you can't see it. So there are some strong similarities between thinking of the universe as a black hole and a black hole as a universe.
Right.
Ooh, that's poetic.
It's really, I like it. That's very cool.
All right.
And this is Colin Brum. Will a photon, from its frame of reference, be able to reach galaxies beyond our event horizon should a photon see time stop for the rest of the universe at the speed of light and therefore not experience, listen, the expansion of the universe along which it is traveling.
Damn,
People are getting,
They're
going in.
Going all in.
I'm telling you, bringing up a lot of stuff here. That's a layered question.
All right, so we have to be careful here.
Right.
We will never see the photon exit the universe. That's the whole point of this, what's going on here. The photon will move away, and it gets swept up by the expansion of the universe, and the energy coming back towards us against the expansion of the universe gets diluted until it disappears entirely.
Okay.
At that point, it's beyond our horizon. We can't see it. All right. As far as the photon is concerned, it's just happily doing its thing.
There. Right.
It's just, it doesn't even know.
It has no idea.
No idea.
It's just happily being.
That's like the famous question with Albert Einstein said, if you're in a car driving the speed of light and you turn on the headlights, what would you see?
Right.
Okay. Well, you can't go the speed of light, but let's go 99.9999% the speed of light.
Right.
You do that, you put on your headlights, you see your headlights.
You see headlights because that's it.
because
It's going out in
everything
front of
is
you.
relative.
It's at the speed of light. It's relative.
You don't even know you're going at the speed of light.
Exactly.
As far as you're concerned, everybody else is passing you by.
Exactly. Yeah.
Which made the awkward joke I told you when Relativity was published. That was it, the New York Times. Somebody made a joke. Hey, Albert, what time does Grand Central Station arrive at the next train?
Right. Right.
So that's the same thing.
That's the same
so
thing.
if you're the photon and you're at the edge, when you're at the edge, that's not your edge.
Right.
When you're at our edge, it's not your edge.
Right.
Any more than a ship going to your horizon, that's not that ship's horizon.
Exactly.
It sees beyond that.
Exactly.
Okay.
Yeah. That makes perfect sense. Right.
Right. And it'll, like I said, and a photon will be absorbed in the same instant it was emitted in its own reference frame.
I love thinking about it like a ship because
Yeah,
that's
good.
so
It works
easy to
great.
envision that
Works
you know
great.
that the horizon.
And you know the ocean goes beyond your horizon.
Exactly.
Right.
Right. Unless you're a stupid flat earther, in which case you fall off the edge, you big dummy. That's what you are. And what you see beyond the horizon is your own ignorance, you stupid ass. Anyway,
Chuck, this is a free country. People think whatever the hell they want.
this is true.
Okay. I don't have an issue with flat earthers. I just don't want them to become head of NASA or something
Well,
like
there's
that.
no
Plenty of jobs for them. Okay.
Yes.
If you want to think Earth is flat.
right. Cleaning toilets is not a bad job. There's a lot of dignity in that, as far as I'm concerned. Anyway, this is Tassos Souris, who says, "Greetings, Dr. Tyson. Tassos from Greece here. How would a civilization living in a planet that is surrounded by black holes from all sides perceive the universe? Will we, from the outside, be able to see them? Will they live their own slowed acceleration time frame?" So a couple different questions.
Yeah,
in
yeah.
there.
So
Couple
the
different-
closer you are to a source of gravity,
Right.
the more time dilated your life becomes.
Right.
So you think you're living a normal life. People from outside see you living more slowly.
Right.
So we will see you living more slowly if those black holes are relatively near.
Right.
That's the first point. Second, if you look out, you will see light bent around black holes. So
Right.
you'll see all these rings,
Right.
these light rings, because that's what the geometry of space-time does when you have a source of gravity and light passes around it. So that's the main difference. The night sky will be these rings.
Yeah.
And Einstein first predicted the existence of rings. They're called Einstein's rings.
Wow.
And then he thought things will never be so perfectly aligned to get a perfect ring. They will never get a ring. And we get some rings, but generally what happens is if it's exactly aligned, you get a ring. If it's slightly off center, it splits into two parts.
Right.
And then if it's off a little more, you can get 4 parts and then 6. And so, but in the limit of a perfect alignment, you get a ring. And so, yeah. Now, that would be dangerous if you're surrounded by black holes. I don't know how stable that orbit would be.
Right. Yeah. Exactly.
Yeah.
You're in a pinball machine at that point.
At that point, you know, as they say, there's no such thing as gravity. Your planet sucks. The black holes suck. They'll
That's
suck suck you in.
Right. All right. Very cool. Thanks a lot there, Tassos. This is John Bickford. Says, "Good day, Dr.
Good
Tyson."
day.
That's what he
Sounds
says.
very Aussie.
Yeah.
Okay.
John Bickford here from Bolton, Massachusetts. The Big Bang, did it disperse matter in all directions somewhat equally? If so, and the universe is expanding in all directions, what happens in the space where the Big Bang happened?
Ooh.
Look at that.
Isaac Newton, my
Yeah,
man.
Right.
And I think I have a finger puppet of him back here. Never understood finger puppets because it's like,
Yeah, now you got your finger up Isaac Newton's ass. That's basically what happens. Just
That's not what I was thinking.
Oh, okay.
I was thinking you can't control the hands or the face or the expression. So
right.
it's kind of
It's the lamest puppet.
the lamest puppet.
Even a sock puppet has more emoting than
Right,
emotes
right.
more than a finger puppet.
Right. I should check. But anyhow, they all look alike back then.
Okay.
It's the colonial era.
There
All the
you
bricks
go, right?
look,
Yes.
they all look colonial.
Put a powder wig on them, and
Powder
who
wig.
knows the difference, right? Just put your powder wig on and your buckle shoes and get to work.
So Isaac Newton argued that the universe must be infinite after he discovered his laws of gravity.
Right.
Must be infinite. Because if it's not, all the matter will find a center to fall to. And it would all fall to form one great heap of mass. But it's an infinite, then there's no one place is not more special than another.
Right.
Now, he didn't imagine that you can live in an expanding universe.
Right.
That was outside of his worldview. Yeah. An expanding universe, you're not all going to fall to one spot because there's a force preventing that.
Okay.
In our case, we call it dark energy. So with that place where the center occurred no longer exists in space. It only exists in time.
Right.
The timeline, if you go back to the beginning of time, on that axis, when you get there, all the matter will be in the same place. You go forward, the expansion of the universe, you don't have access to that point in that space. Gotcha. So I'll give an example. So if you have a balloon and you're inflating the balloon,
right?
You start out, the balloon is like tiny.
Yeah.
Right? That's the Big Bang. Okay? Right. Or the whole balloon is in one spot right there. Now you start blowing on it, it expands away from that spot.
Right.
Is that spot on the surface of the balloon? No. It's in the center of the balloon. How do I get to the center of the balloon? Turn back time. And the balloon gets smaller and smaller and smaller. Now you're back at the center.
Right.
So
you'd have to shrink the universe
by going backwards
in time.
Exactly. So the center exists, but not in the space coordinate. It exists in the time coordinate.
There you go.
Yeah.
Really?
Deal with it.
Yeah. These people are asking really good questions, man. I got to tell you.
This is not up his ass. He's got a jacket. He's got a red coat on.
I don't know what jackets you wear, but at the hem of my jacket is my rectum.
Now you ruined finger puppets for me. I don't want to play with finger puppets anymore. We get through a lot of questions today.
We are.
More than usual. Okay.
This is Ilyas Siametis. Ilyas Siametis.
That does not sound right, but we'll go with it.
Yeah.
You can put a little flavor in it.
Okay.
Ilyas.
Yes. Siametis.
Okay. Go.
Dr. Tyson, Lord Nice, Ilyas here from London. Would it be theoretical?
London, Ontario? London, Connecticut? London?
Hey, man, he just says London.
Okay.
So,
is there a London, Ontario?
I don't know.
It kind of feels like there would be.
It feels like there's a London everywhere.
Doesn't
That's
feel
just,
like it?
yeah. There's a.
You know what that is? That's lazy ass Brits coming to the new world.
Where did we come from? We came from London. Where are we now? London. Why not?
No, let's call it New London.
New London. There you have it. Hip, hip. All right, so he says, would it be theoretically possible to break the bonds between atoms of something and reconfigure them into something else? Let's say manipulate the billions and billions of carbon atoms in a wooden chair and make a table instead. Strong emphasis on the word theoretically.
Yeah, that's not interesting, though.
Okay.
To turn a wooden chair into a wooden table?
Well,
you're not really manipulating atoms. You're just
reassembling
the macroscopic, the wood.
Right. That's all you're doing is taking the wood and moving it around.
You're moving the wood around.
Right. That's it.
If you want to change molecules, do something fun.
Right.
What you want to do is take your molecules and rearrange them and make an alien.
Right.
That's still alive, but it's not you. It's some other thing.
Right.
Do something interesting. If you're going to have power over molecules and atoms. Now, what chemists do is, because we don't have tools to pluck atoms and reattach them, we put them in vats of other chemicals that make
a reaction.
Make a reaction.
Right.
And these are called catalysts.
Right.
Okay. I want this molecule and I got that molecule, put in a catalyst that makes that.
Boom.
Okay. And does that natively and naturally. So that's how we're doing that today.
Okay.
So yeah, do something better than a chair to a table.
Right.
And yeah, but in principle, you can turn it into anything organic.
Right.
Because if you can use the molecules of life, That's organic chemistry. Why not make something else organic?
I love the idea. Okay. Well, there you go, my friend.
Yeah.
All right. This is Aaron Turetsky. Says, hey, Dr. Tyson, Lord Nice, Aaron here from Staten Island, NYC.
All right.
He says, my question pertains to the way that we visually display Earth in globes, maps, and elsewhere. Since magnetic poles flip and the Earth's landmass are constantly shifting, is there any scientific reason that we decided Antarctica would be at the bottom or the South Pole? I understand that human civilization happens to exist while a majority of the land is in northern hemisphere, so our maps are northern biased. But what does science have to say? For example, if an alien civilization was to look at the Earth through their telescopes, is there any reason they would know that Battery Park is at the bottom of Manhattan and not the top? Wow. My man got a problem with globes.
And plus, he mentioned Battery Park because one way to get to Staten Island is through the Staten Island Ferry,
which
out
is
of
in
Battery Park.
Yes.
So that was not a random reference. That
but who wants to go to Staten Island? Come on, man.
So what does science have to say about it? First of all, at the beginning of the film, Happy Feet, where does that take place?
At the
it's penguins, so there's only one place it can take place.
South Pole.
South Pole.
Penguins.
Antarctica.
Antarctica.
The camera moves in on the Earth.
Right.
And of course, North Pole is up and South Pole is down. But this entire movie takes place at the South Pole.
Right.
So as far as they're concerned, that's where the action is. So you know what this movie does? Instead of going down to the South Pole, the entire frame rotates 180 degrees.
Nice.
And you go straight on in to Antarctica.
Okay.
That was a point of view shift.
That's pretty
cool. You know who did that movie? Happy Feet, George Miller, the same guy who did Mad Max.
A little departure from the Mad Max.
He's got range.
Yeah, he certainly does.
So scientifically, we use the right-hand rule.
Okay.
So stick out your right hand.
Right.
Open palm open.
Palm open.
Now make a curl your fingers. Keep your thumb up.
Thumb up.
Okay. Any object that's rotating in the universe, if you curl your fingers in the direction it's rotating, your thumb is the North Pole.
That's the North Pole.
Yes. For any object anywhere. Correct.
Okay.
If you want your thumb to stick in the direction of the South Pole, you have to use your left hand.
Oh, that's okay. So the right hand rule is right hand. Thumbs up.
That's how you know what North Pole is. And if you know what North Pole is, you know what South Pole is.
You know where South Pole is. Okay, gotcha.
Okay. Yeah, so yes, of course we are north biased, but there is at least consistency with all maps show north.
Okay.
North up.
All right. It's pretty cool. I'm going to tell you the truth. I don't care.
And by he mentioned the magnetic pole.
Now
when I grew up, how old I am, magnetic pole was in the northern territories of Canada.
Wow.
But it's been shifting.
It's been shifting, right?
Yeah, because North Pole is a wandering thing.
Yeah.
And right now it's passing the North Geographic Pole.
Okay.
It's just closer to that than it's ever been before. And it's headed towards Siberia.
There you go. So it's actually where it belongs, where we say it is.
Right now,
is the North Pole, the Santa Claus Pole.
It's near the North Pole.
It's near the North Pole.
And Putin is going to have control over the North Pole.
Well, then say goodbye to the magnetic field, people.
Hello, StarTalkiverse. Neil deGrasse Tyson here, your host of the StarTalk podcast. I'm here to announce that we just opened a brand new channel on YouTube called StarTalk Plus. And that's where we're going to bring all kinds of innovative content that doesn't quite fit on our flagship channel, but they will involve experiments in what we create, what your reaction might be to what we create, and it's going to be our skunk works, as it were, to borrow a term from aerospace. So I look forward to sharing all of this new content with you, and check it out if you have a chance. What do you got next?
All right, here we go. This is Mile Milkovsky. Speaking of Putin. Okay, Mile says this. Hey, Neil. Hey, Chuck. My name is Mile. I'm from Macedonia, Balkan, Europe, world.
I like that.
Yeah,
okay.
That's very cool. He says, we see a lot of matter goes into energy in the universe, but do we see the other way around, energy becoming matter?
Yes. Oh, yeah. Well, yeah.
Okay.
Yeah.
Okay.
So, in the sun, in the center of the sun, there's thermonuclear fusion. Hydrogen nuclei merge.
Right.
Okay. So, here's what happens. Ready? a hydrogen only has one particle in its nucleus,
Right.
a proton. So there's just protons there. So you have one proton meets another proton.
Hey, how you doing?
Okay.
What's up?
Hey, there you go. How you doing?
Right.
Okay.
How you
now,
doing?
protons have like charge.
Right.
So like charges do what?
They don't like each other.
They repel.
That's right.
So in order for them to get close together, they have to be moving so fast that their speed overcomes their repulsion. And they're so close to each other
Right.
that a whole new force that's strong has to kick in.
Oh.
You know what we call that?
An arranged wedding.
We call it the strong
The
force.
strong force.
Yes,
Right.
it's sensibly titled, the strong force. In that moment, one of those protons becomes a neutron.
Oh,
It transmutes. So you have a proton and a neutron.
I don't need that woke atom in my life.
So what? Transitions.
Transitioning atoms. Who needs that?
Wait a minute. We started with a positive charge.
Right.
Now there's a neutral charge. What happened to the positive charge? You can't just pocket that.
Right.
Okay? A particle comes out carrying away that charge.
Okay.
It's the antimatter version of an electron
Whoa.
called a positron.
Positron.
Okay? Now, this is a soup of ionized atoms. Right. And when you're ionized, electrons are flying everywhere. If you're a positron and you're antimatter positron,
Right.
if you see an electron, that's all she wrote. You
Right.
annihilate
Look at that.
instantly,
Instantly.
creating energy in the
Look at
center of the sun.
Look at that.
That's one of many ways the sun is generating energy in the core.
Wow.
That happens every moment of every day. Two particles of matter coming together and creating pure energy.
Look at
The
that.
positron and the electron in the core of the sun.
That is amazing.
So yeah, but it doesn't happen around the house.
No. No.
But it would.
If you had a son.
A sun, S-U-N.
Right.
Yes. So now watch.
Not that lazy guy that's on the couch playing video games all day long.
Is that what your son does? That sounded too close to home, Chuck. Chuck, you got with your 17-year-old son.
Yeah, exactly.
So here's the thing. Light that we use, visible light.
Visible light.
If you look up how much energy a red light photon has or a blue light photon, just look up how much energy that is. There is no particle that can be made with that much energy because it's not enough.
Okay.
So light, visible light stays visible light its whole life.
Wow.
Increase the energy up to beyond ultraviolet
Ooh.
into X-rays.
X-rays.
Ooh. Now ask yourself, what is the energy of an X-ray photon?
Mm-hmm.
It's about the energy of an electron.
Ooh.
So you can have a field of X-ray photons with electrons spontaneously being created within it.
Oh.
Okay?
Okay.
Now, but you can't just create a particle out of nothing. You also have to have the antiparticle.
Right. Okay.
So if you create electrons, you're also creating what?
The positron.
Positron.
Right.
There you go. And so that's energy
And it
becoming
being
matter.
Matter.
Right.
Look at that.
That's the inverse of that he was asking me about.
Yeah, exactly.
And then they find each other again and they become matter. This soup was going on in the early universe in every cubic centimeter of the universe.
Look at that.
Matter going back and forth
Just-
until the universe cooled,
Right.
where none of the photons left had enough energy to make particles.
Oh, Lord, I'm so tired.
And we froze out the total number of particles in the universe in that moment.
Look at that.
No longer could you make more particles.
That's it.
That's it.
That's great.
This is like the first 3 minutes of the Big Bang.
Wow. That's so, oh man.
Yeah.
3 minutes.
That's the first 3 minutes.
Look
Yeah.
at that. That's amazing.
So in my book, Astrophysics for People in a Hurry, the first chapter, it was something like in the beginning or something, or it begins with that.
Right.
And I take you through those details. The conversion of matter, energy, and it cools down, all that's happened.
That's very, very aggressive, the title in the beginning. Just saying that association is,
Well, where else am I going to begin the story but in the beginning?
this is true. You know, I'm just saying that those words kind of bring to mind something else.
That's an old joke from elementary school.
What's that?
How do you know God was a baseball player? Loved baseball?
I've never heard of
Because
this.
he began it in the big inning.
That's a rough one, man.
it's
Even God is just like, let me handle the humor.
the humor.
He's like, stick to prayer. Humor's my thing. Okay. Okay.
Sit this one out.
Yeah. All right. Let's go with Andrew Coffey. And Andrew Coffey says, "Good day, Dr. Tyson and Lord Nice. Wishing you a wonderful wisdom from a few fine fellows. Andy C. here from Vancouver, British Columbia.
All right.
I've always
That
wondered."
would be Canada.
That's
Yes.
right. "I've always wondered, how did we first calculate the speed of light in a vacuum? And how do we know it's a constant? Is it possible we could be wrong?"
Oh. Speed of light in a vacuum.
Yes.
Okay. Galileo is the first one known to try to measure the speed of light.
Look at that. Wow.
So he put somebody on.
What an ambitious dude he was. That dude was ambitious.
My man.
Yeah.
He's my man Galileo. At night, he put somebody on a mountaintop with a lantern and a little shutter.
Right.
Okay. And somebody, he was on another mountaintop with a lantern and a shutter. And they said, when you see one,
give it back to me.
Give me the signal back with the shutter. And he concluded, light, if it's not infinitely fast, it's faster than we can measure. Okay.
Nice job, Galileo.
Just tell it like it is.
Nice job, right.
That's all you know.
Yeah, that's it. That's what we know right now.
Can't tell more than what you can know.
There you go.
Okay. So, do you know the distance from Earth to the center of the sun? I mean, to the sun?
93 million.
Okay, so twice that is?
186
million
miles.
Miles, okay? Keep that number in your head.
Okay.
Okay? That's the baseline of Earth's orbit around the sun.
All right.
Okay. A guy named Ole Romer.
Okay.
Ole Romer. It's got one of those umlauts with the O-E, okay?
They just called him Old Rome back in the day. Old Rome. Hey, what's up, Old Rome?
We can't pronounce your name. We just call you Old Rome.
Old Rome.
No. Ole Romer.
Okay.
At the time he did this, we knew that the Newtonian gravity not only described the moon around Earth, Earth around the sun, it described Jupiter's moons around Jupiter.
Okay.
So you didn't have to be the sun to be the center of gravity for a system. It worked for Jupiter too. So this was a testament to the universality of Newton's laws. Because if it just works for the Earth and Moon, maybe it's just Earth and Moon.
Right.
You don't know that it works everywhere else. It works everywhere else.
Okay.
All right. So you calculate when the moons pass in front of and behind Jupiter.
Okay.
What he found was that when Earth was closest to Jupiter, the eclipses occurred 1,000 seconds sooner than when Earth was on the opposite side of the sun from Jupiter.
Okay.
He said either Newton's laws are wrong, or we had to wait for the light to cross the entire orbit of the Earth to get to you. Because on the back side of Earth, it was 1,000-second delay compared to the front of your orbit.
Right.
So, what's the formula for speed? Distance divided by
time.
Time. What's the distance?
186 million miles.
What's the time?
1,000 seconds.
What is the speed of light?
Very fast. Very, very fast.
Take those two numbers, you divide them, 186,000 miles per second. Now, we didn't have the diameter of the Earth. The guy had the wrong number for that. It was the most accurate estimate of the speed of light yet to be made. Just the delay in the eclipses of Jupiter's orbits.
Right.
Depending on where you are in our orbit when you're taking a look at them. And the numbers turn out all nice and even, right? 186 million miles, 1,000 seconds, everything was clean and easy.
Right.
Okay. Now we're sophisticated. We can measure it in a laboratory. We can do what Galileo attempted to do. Sure enough, we get the same number.
Look at that.
Okay? Every time we've ever measured the speed of light, we get exactly the same number. At all times.
At all times.
Correct. And we look in other parts of the universe where we see phenomenon happening, speed of light's the same. Right on up to the edge of the universe.
Cool.
So our evidence, and since as you look out in the universe, you look back in time, we can say with confidence that the speed of light is the same and unchanging across space and through the depths of time. It is the most fundamental constant of nature we know.
Yes. Yeah.
It is so fundamental that we define the length of the meter in terms of the speed of light.
Wow. Okay.
So if we make an extra measurement of a decimal place in the speed of light,
Okay.
that affects the length of the meter. That's how badass the speed of light is.
Right.
It's running the show.
Look at that.
So a meter is how far a beam of light goes in 1/30 millionth of a second. Yep, it's the right 12 decimal places.
Wow.
Yeah.
That is super cool.
Now, the speed of light is different in the air and in water and in a diamond, but in the vacuum, that's the speed.
Right, that's the speed.
Yeah.
Right.
And 186,282 miles per second.
Wow.
Or 3 times 10 to the 8th meters per second. But it's really it's like 29,990,000. We round that up. It's a nice rounding to 3 times 10 to the 8th. So that would be 300,000 kilometers per second.
Okay.
And now you make meters and centimeters out of that.
Out of that.
Right. And so, but it's really like 299,000 something. It's close, but we round it up to 300,000 kilometers a second. 186,282 miles per second.
But the best measurement of it is Muhammad Ali.
Oh, yes. Take us out with Muhammad Ali.
I'm fast, I tell you. I'm so fast. I turn the light switch off. I'm in the bed before the room get dark.
Oh. Okay. Muhammad Ali is faster than the speed of light.
There you go.
As evidenced by that very important data point right there. Chuck, that's all the time we have.
Oh, that was fun.
Well, man.
A lot of fun.
Oh, grab bag.
Grab bag.
Grab bag.
Or galactic gumbo.
In the cosmic crib. Because we're back live in my office.
That's right.
At the Hayden Planetarium. All good here. We're done with this latest episode of Cosmic Queries. Thanks for joining us. Neil deGrasse Tyson. Keep looking up.